Welcome to the YetiPlow design overview. This project was sponsored by JND Snowplowing Incorporated out of Wyoming, Michigan. Here you can see the YetiPlow, a municipal tractor designed for removing snow specifically from city sidewalks. When JND Snowplowing came to us, they had two major problems. The current equipment in their fleet is getting old and hard to maintain, and new equipment is extremely pricey, ranging from $100,000+ per machine without implements, and there isn't one machine that satisfies all their needs. They currently use mostly the Bombardier SW48 pictured on the left. They also use trackless MT5 articulated tractors pictured in the middle and Case Farmall 110N tractors pictured on the right to remove snow from city sidewalks. J&D provided us with a list of constraints and specifications for this project. We had to design and build a prototype tractor. It must contain favorable features from all three machines currently used in their fleet. It could be no wider than 50 inches, no taller than 85 inches, and no longer than 135 inches. We had a minimum weight requirement of 5,000 pounds. The machine had to be wheeled. It had to include operator comforts such as an air ride seat and cabin. The machine had to be hydraulically driven, and it must include front and rear PTOs. The reproduction of cost of the machine was around $50,000, and it must accept multiple implements such as V-plows and snowblowers. And the machine had to have two speeds, a cruising speed and a plowing speed. COVID-19 caused our timeline to change. The build portion of this project was no longer required due to extended lead times. Alternatively, the team proposed a plan to J&D by refining our CAD design. Refinements to the internal cabin layout were made. Exterior and interior aesthetics were modified. Design for assembly features were included. Professional drawings packets were provided, and we provided CAD changes upon request. We also refined our documentation to standardize a build plan. We identified any key locations where failure may occur, and we also provided a maintenance schedule. Overall, the project met all specifications provided by J&D, with an overall designed length of 135 inches, a width of 50 inches, and a height of 84.5 inches. We exceeded the minimum weight with an estimate of about 6,375 pounds. The machine used wheels over tracks. Operator comforts were included. The machine is hydraulically driven with hydraulic front and rear PTOs, and the project came in about $5,000 under budget. Some of the challenges we faced along the way were little knowledge about hydrostatic drive systems. We had little knowledge about tractor components such as articulated axles and air ride suspension. We had little knowledge about engine mounting design and almost no knowledge about four-wheel steering geometry.
So for the YetiPlow, we had 5 primary systems that we had to design to meet the functional requirements stated by our customer JND. These include the suspension and steering system, which are sort of self-explanatory, a air ride cabin suspension to minimize vibration and harshness felt by the operator, custom cabin for operator comfort, a skid plate to protect the undercarriage of the vehicle, a hydraulic system to replace the conventional transmission and redirect power through hydraulics rather than through mechanical means, and then engine and engine mounting to figure out how we're going to hook the hydraulic system to the engine and how we're going to mount the engine to the plate. Touching into the suspension system, we used a design commonly found on agricultural tractors where the axle is connected to the frame by a central pin that the axle is able to pivot about. There's coilover shocks on either side to control the articulation of the axle assembly, as well as hard stops to limit the maximum amount of travel that can be seen. Our axle design used a outer diameter that was initially specified by J&D. We varied the wall thickness and figured out how thin we could get it without having issues with it failing.
The air ride cabin suspension was based off of conventional semi-truck air ride cabs. These systems commonly use a combination of air springs and hydraulic shock absorbers. The front of the cabin is hinged on an elevated block as shown in the right figure. 2 rolling lobe air springs and hydraulic shock absorbers are mounted in the rear of the vehicle on each side as shown in the left figure. The air springs isolate the vertical movement while the hydraulic shock absorbers dampen vertical oscillation during the operation of the vehicle. Both were selected with the help of industry experts once parameters such as the gap between the cabin and the base plate and the overall weight of the cabin assembly were determined.
The hydraulic system found on the YetiPlow is quite complex. Ryan Behringer of Federal Fluid Power was the contracted lead designer for the YetiPlow's hydraulic system. He worked closely with the team throughout this project to spec out components and develop the hydraulic circuit based on our needs. Overall, there are many components that make up the YetiPlow's hydraulic system. 4 steerable Lane hydraulic motors with parking brake are attached to each one of the 4 wheels that drive the YetiPlow in forward and reverse. A set of tandem pumps that transfer fluid to the 4 motors is attached to the bell housing on the motor located at the center of the vehicle. There is 1 pump for each set of motors, meaning that the front 2 motors and the rear 2 motors are in parallel with each other. There's also an auxiliary pump attached to the tandem pumps that drives the steering and open loop functions on the YetiPlow's hydraulic manifold. This auxiliary pump is first ran through a priority valve to give steering capabilities priority over any items ran by the hydraulic manifold on the YetiPlow. This means that the YetiPlow will always have steering capabilities and the steering cylinders will never be starved of fluid during operation. An MS Hydraulics hydraulic steering orbital is used to direct fluid flow to steer the YetiPlow when the steering wheel is turned. The manifold on the YetiPlow powers open loop functions such as the front and rear hydraulic PTOs, front and rear implement lifting cylinders, the direction in which snowblower chute points, and the pitch at which the snowblower chute shoots the snow when removing snow from sidewalks. All fluid in the system is then ran back through a heat exchanger to cool the fluid before being filtered by an internal tank filter so the fluid can be used later on.
So moving into the engine and engine mounting systems, JND provided us with a Ford 300 inline 6 engine, commonly found in the Ford F-150. They also asked that for the purpose of using existing resources, we try to incorporate the mounts that are used on their bombardiers, which these mounts are used for mounting the engine below the frame plate versus in our design we have the engine above the frame plate, so we needed to see if it would work for us to invert these mounts.
This project utilized Solidworks to carry out the 3D modeling for the design. This allowed us to ensure that all of the parts were accurate and fully dimensioned. With this creation, we were able to add parts to assemblies and ensure that they were able to fit together correctly. Once created, we were able to move on to manufacturing drawings, in which we were able to fully dimension these drawings so that a manufacturer could create them correctly. Each of these individual parts was then combined into the main assembly of the YetiPlow. This main assembly can be seen here. Within the main assembly, this contained many subassemblies. The purpose of this was to allow the subassemblies to be manufactured simultaneously, and then the subassemblies could then be put together at the end to form the final altogether assembly seen here. One of the subassemblies can be seen as an example here. As you can see, there is a large number of parts even within a subassembly. Each one of these subassemblies had its own manufacturing print packet created, and in this print packet there was instructions to follow so that it could be created just as in the CAD model. Not only did this provide for a nice looking model, this also allowed us to prove concepts, such as the example shown here. The lift on the tires was to be limited to a 3-inch maximum minimum, so we were able to confirm that with the model. Another example would have been the steering, in which we were able to confirm any interferences that may have occurred as the steering cylinder moved from side to side with its maximum reach. With certain mating techniques used in the assembly, we were able to actually see how the assembly would move in real life in the SolidWorks assembly. Using this technique, we were able to confirm certain aspects of the design, such as the turning radius, as shown here.
We ran some basic FEA and noticed that the stress distribution in the mounts, as shown in the bottom pictures here, on the conventional mounting, you can see that it's kind of a symmetrical stress distribution where both sides of the mount are placed on in similar stress distributions, versus when we invert it, we place the active side of the mount under more stress distribution, which would make the mount wear significantly faster, and you wouldn't get the vibration isolation that you get out of it either because it's out of orientation. So We recommended that they either design perches to meet it so that they could maintain the conventional mounting orientation, or we just cross-referenced the engine to a Ford F-150 and found mounts that account for mounting to a lower surface and provided them with plans to design perches that would meet that as well. Now on the screen are some of the calculations that we did. We considered wide open throttle conditions, cornering conditions, impact of curb, that sort of thing. Kind of figured out what our worst case scenario for stresses were and then varied the thickness based on that stress distribution. We presented the customer with two separate cross sections that they could potentially use for the axle assembly and recommended that they use the square one because it was significantly stronger.
As previously mentioned, this is the plate the front of the cabin will hinge on. We assume the cabin weighs about 1,200 pounds, and although it is back heavy, for this analysis we assumed the plate will be supporting a static load of 600 pounds just for a worst case type of approach. This yielded a maximum stress of 395 psi, with the material yield being 36 ksi. So with this we are at about 1% of the yield, therefore this should work out just fine. So this slide is just saying how our sponsor requested a 2-inch structural steel skid plate. As for the cabin, we got our idea for the cab layout through benchmarking mostly the Bombardier. This included a 12-gauge square tubing roll cage plus cross members for added support on the walls. A large front and rear window was also included to maximize visibility, as well as a gauge cluster, switch panel, and hydraulic control levers. This is the completed analysis for the floor of the cabin. That square you see there is a representation of the mounting plate for the seat where 400 pounds was applied to the 12-gauge sheet metal floor plate. There are also crossbars under the floor plate to support the load shown in the lower image. It can be observed that we are nowhere near reaching yield, so this is a good design. This analysis was performed to test the structure of the roll cage as if the machine were to be tipped onto its side. Assuming the overestimated weight of the cabin at 1,600 pounds will be acting downward as shown in the image, this was the resulting analysis. Based on the analysis, the stresses on the roll cage reached 719 psi, where yield is 51 ksi, so it should have no problem withstanding this load.
The scope of this project also includes the sourcing of all components used for the building of the machine. A list of suggested suppliers was provided as a starting point at the beginning of the project. We then worked directly with those suppliers to crawl out what they were able to provide. A couple of alternative renders were used for the parts that were not available from the provide list. Much of the hardware was quoted using McMaster-Carr. This provides an excellent way to download 3D models to help ensure the design was proper. Much of this is standard hardware that could be purchased from local hardware stores. For interior components such as gauges and switches, Summit Racing was the primary vendor of choice as they provide a wide selection of vehicle components. When sourcing these components, there was a large emphasis on ease of access. Time is of essence for this line of work. If a component was to break or malfunction, JND plowing needs to be able to quickly repair and get the vehicle back out on sidewalks. Included in the final deliverables was the complete list of source components for ease of ordering when building the machine. The total cost of the project is about $43,500. It includes the cost for frame materials and every primary systems, such as the hydraulic system, suspension system, air ride system, steering system, electrical system, and machining. The cost of the engine is not included because JND is donating the Ford 300 engine to the project. The material cost is then marked up 15% to include the cost of any logistics and taxes, which give us the total cost.